Section 1. We are going to start what is called discrete mathematics, which, if you think of a continuum, which means something that is continuous, if you think of a number line, are there any gaps in this number line where numbers don't exist? No, there aren't. Let's see if I can count in the negative direction. There are no gaps. It's really continuous. When we say discrete, we're not talking about continuous. We're talking about unique values, such as integers. These are discrete values. They are not continuous. They're specific values with gaps in between them. When we talk about discrete mathematics, we're going to talk about specific values, not a continuous thing. That's really all that discrete means. So there's different things that fit into what are called discrete mathematics, and we are going to start off delving into the idea of probability. And before we can get into probability, we have to know how to count. So, how many different ways can three distinguishable objects, which means they all look different? I haven't given you three red pens and saying how many ways can you rearrange them, and it all looks the same no matter how you do it. These are three distinct objects, three different colored pens here. How many ways can you rearrange it? So one way is we can form what's called this tree diagram. And if I start, here's my first arrangement. I have an A, and I have a B, and I have a C. These are my objects. And I could start with the A, and then go a B, and then a C. Or I could go A, and then a C, then a B. So if I start with an A, there are two other ways that I could do the B and the C. Or if I started first with my B object, then I could go AC or I could go CA. So there are two ways that that can happen. Whoa, how did I get a 2 and a 2? So there are two ways that that can happen. And if I started with a C, I could do AB or BA. So there's two ways that can happen, making a total of 1, 2, 3, 4, 5, 6. If I counted out the end of all those branches on that tree. There are 6 different ways that we can arrange three objects. So a tree diagram, they don't even say that here, a tree diagram is one way of laying out all the ways it can happen. Now mathematically, there is a way that we can calculate it without having to draw a picture. And it's called the principal accounting or the fundamental accounting principle. It says if I have 3 different sets, and set 1 can be arranged in R1 ways, and set 2 in R2 ways, and set n in Rn ways. And to get the total number of ways, I simply multiply them all together. So, if I have a license plate from Tennessee, it happens to have 3 letters of the alphabet, and then it is followed by 3 numerical digits, 0 through 9. What are the different number of license plates that can be formed? Well, how many different choices do I have for that first position? I have 26. And how many choices do I have for the next position? I have 26. And 26. So I multiply them together. And then I multiply them by 10, 10, 10, because I have 10 digits and 10 digits and 10 digits. Now, obviously, you could shorten it up and call it 26 cubed times 10 cubed. Why don't you run a calculator and tell me how many different Tennessee license plates they can manufacture with this arrangement of letters and numbers?
17,576 billion.
Got the number?
Oh, sorry, I said it wrong. 17,576,000.
All right. Let me take off these zeros. That the number?
Yeah, that's it.
There you go. 17,576 different license plates can be manufactured with this arrangement. Now, that is allowing us to use C and then C again and then C again if we wanted to, because that would be a unique thing. So if there are no restrictions. But if we say, hey, no letter or digit can be repeated, then the very first letter, I have how many choices? 26. And the next letter, I have 25 because I've used up a letter, and then 24. And then I get to my first number, and I have 10 available, and then 9 available, and 8 available, and that makes, how many license plates can you manufacture in that scenario?
11,252,000.
So a few less, still a lot of license plates, but a few less if you restrict it. So in order to count, we just figure out the number of ways I can do one thing, times the number of ways I can do the next thing, times, we just multiply it all down. That is called a permutation, when we want to know the number of ways we can arrange in objects, or the inset. So the order that they can happen. Now, a permutation of just 3 things or 7 things can be found by using factorial. Do you remember what factorial means we do?
Oh yeah, 9 times 8 times 7.
Yes. If I said 3 factorial, that means 3 times 2 times 1. If I say 9 factorial, it means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. There it is. So if we go back up where they ask us to take 3 distinct objects and arrange them, what was the answer to it when we did the tree diagram? 6. There were 6 different ways we could do it. Well, what is the answer to 3 times 2 times 1? 6. So it's called a permutation. So if I have 4 students sitting in these desks, and I say, how many different ways, remain the same desk, how many different ways can I arrange you 4 students in order? How many different orders can I arrange you 4 students? 4 factorial. I don't know, what's 4 factorial?
I haven't put before, I forgot what it was now.
There is one. It's under math on the graphic calculator. It actually takes longer to do it probably than just 4 times 3 times 2 times 1. 4 times 3 is 12, times 2 is 24, times 1 is 24. We don't need a calculator. There are 24 different ways you 4 students remaining in these same desks could be rearranged in different orders. 24 different orders. Now remember, if all I did was switch Nate and David, that's a different order for the group. Distinguishable permutations. Sometimes we have groups where 2 of them or 3 of them look the same. So how can we figure out distinguishable permutations? Well, here is the idea. If I have n objects, well, n factorial is the way that I can arrange them in different orders of permutation. And then I need to divide out all the orders of things that look the same. So if the n1s all look the same, I have to take n1 factorial. What does that mean? Let's apply it down here with letters and words. Count the number of different 9-letter words, don't worry about whether the word's in a dictionary or not, that can be formed using the letters in each word. Well, part A here, are every one of these letters different in Dragonfly? Yes. So if there are 9 letters and they're all different, there are 9 factorial ways I can rearrange that. How many is that? You may want to find, and on a graphing calculator, you hit 9 under your math menu. No. Yes, and then probability. You have the math menu, then go over to PROBE, probability, and you'll find the factorial.
I got 362,880.
362,880. 0. That it? All right. So 362,880 different ways you can rearrange the letters in the word dragonfly. Part B, in butterfly, do we have repeating letters? Yes. So I still do my 9 factorial, but now I need to start dividing. What's the first letter that repeats? Well, T. There are 2 T's, right? So I need to take those 2 and divide out the order that I can do those 2. Are there any other letters to repeat? No. Get that answer. 9 factorial divided by 2 factorial. And by the way, 2 factorial is just 2. You could take the previous answer and divide by 2. What do you get? Okay. Half as many ways. Then we get over to bumblebee. There are still 9 letters, so originally 9 factorial. What's the first letter that repeats? B. How many times? So I have to divide out 3 factorial. What's the next letter that repeats? E, 3 times. Now, I'm going to do a little simplification of this before we go to a calculator. If I start writing this is 9 times 8 times 7 times 6 times 5 times 4 times 3 factorial. I went to 3 factorial because I can just cancel that one out there. And then the other 3 factorial I called 3 times 2 times 1. 3 goes into 6 twice, and then those 2's are gone. You could go 9 times 8 times 7 times 5 times 4, and it will be this answer. Or you can do it on your calculator with your factorial button. What is the solution?
10,080.
10,080. So every time we have more repeating or non-distinguishable, we can't tell them apart, then there are fewer and fewer different orders that we can actually tell are different from each other. So that's not a hard concept either, hopefully. Now, let's, instead of saying we've got 4 students and I'm going to take all 4 of you and rearrange you, we're going to say we have 4 students, but I'm only going to take 3 of you and rearrange you, instead of taking the whole group. So that's still a permutation, because we're finding the number of ways we can order or arrange something in objects taken R at a time. So right here is one of the common notations. There are other notations. Another way of writing that is this way. That's another way of writing it. We'll use the one the book does. In things taken R at a time. So the formula for it, right here. In factorial, it's still the number of ways I can order those n things, but then we take n minus r factorial on the bottom. So we're going to use this formula to start off with right down here. It says evaluate each expression. Now when they say without a calculator, we have a permutation button on the calculator that we'll get to, but we're not going to use the permutation button yet. So if I have a permutation of 6 things taken 4 at a time, that's 6 factorial divided by 6 minus 4 factorial, which is 6 factorial divided by 2 factorial, which is 6 times 5 times 4 times 3 times 2 factorial over 2 factorial. I'm going to cancel those out. 6 times 5 is 30, times 4 is 120, times 3 is 360, right?
Yeah.
We didn't need a calculator. 11 things taken 3 at a time. 11 factorial divided by 8 factorial. Where did my 8 come from? 11 minus 3. I just didn't write it down like I did over here. I just went directly to that. Now this again, that's not hard. That's 11 times 10 times 9 times 8 factorial divided by 8 factorial. 90 times 11, 990. Is that right? See, we don't need calculators. N things taken 3 at a time. A permutation of n things taken 3 at a time. Can you tell me the formula? Factorial.
Factorial over n minus 3.
And that's all we can do because we don't know what n is. There's our answer for that one. So we really didn't need a calculator on anything. Now down here, we'll actually use our permutation button in a minute. We'll go find it. But it says 16 answers. 16 actors answer a casting call to try out for roles as dwarfs in the production of Snow White and the 7 Dwarfs. In how many different ways can the director cast the 7 roles? So we have a permutation because the order matters. I mean, the first one's sleepy and then dopey and then dumpy and grumpy and I don't know what they are, but whatever they are. We have 16 of them, but we're only choosing 7. So a permutation of 16, taking 7 at a time. Go to your calculators, and I'll go through the graphing calculator one, but any scientific calculator has it. In fact, graphing calculators are harder to do than just a scientific calculator on this. But I'll pull up the scientific calculator. And under the math menu and under probability, you will find this, but you have to enter your first number before you go find that stuff. So I have 16. So, whoops, let me hit clear again. Clear, clear. Maybe I need to hit quit. There we go. I do 16, then I go to my math menu, I go over to probability, and then I find right there NPR, a permutation of n things taken at a time. And there it stuck my 16 in, and now I can stick my 7 in, and now I get my answer. So when you are the casting director, there are, what is that? Put my commas in. 57,657,600 different ways you can cast 16 people in the role of 7 dwarfs. I would like you to list them. No. All right. Combinations. Combinations are where we're choosing a small subset from a larger set, but we don't care the order. So what would that be? Well, you're working in the cafeteria, and there is a whole barrel of potatoes, and Mrs. Mason said, pull out 200 of those potatoes to peel. Well, maybe there's 1,000 potatoes. We want 200 of them. It doesn't matter the order that those 200 potatoes are in. They're all just going to go and all mashed together to be mashed potatoes. So we don't care about order in that case, and there are other things where we don't care about order. That's called a combination. So combinations, we can have n objects and only take them r at a time as well. And here is the formula. Now I want you to notice this part of the formula is exactly like the permutation formula. Then all we are doing is dividing out the order of those r things, because in a combination we don't care about the order. So just like when we had in Bumblebee, those 3 bees, the order won't make any difference because each bee looks like the other, and we just divided it out. That's what we're doing here. We're just dividing out the order of the things that we are drawing out. And so the combination formula is derived from the permutation formula. So first of all, we need to know, when is it a combination and when is it permutation? Combinations, the order does not matter. Permutation, the order does matter. A president, a vice president, and a secretary are chosen from a 25-member garden club. So does the order matter in this one? Any ideas? Yes, because these are all unique places. This would be a permutation. From 25 members in the club, we are going to be selecting 4 of them, and the order matters. First one's president, second one's vice president, etc. So this is a permutation. A cook. Oh, why did I use potatoes? Chooses 5 potatoes from a bag of 12 potatoes to make up a potato salad.
Why was it 4 if there were only 3? Like
1, 2, 3. That is a good question. There are only 3 positions. I was thinking we had 4 positions. B, permutation or combination? This is a combination. The 5 potatoes, we don't care which ones you chop up first. It makes no difference. So this is a combination. Total of 12. We are taking 5 of them at a time. Teacher makes a seating chart for 22 students in a classroom. There happens to be 30 desks in that classroom. David, you wait here and with us.
Well, I mean, all the desks are the same, so it's a combination. I don't know.
So the question is, does order matter in a seating chart? Does the order of the students matter? Yes. The order of the students matter. So this is a permutation. And why don't you calculate this one for me? There are 30 desks, but I'm only going to fill 22 of them. I have 30 desks in this room. One of my classes actually has 22, I believe, students in it. How many different seating charts can I make?
6.57 times 10 to the power of 27.
6 point what?
57.
Is that what you got too, Lily? Rounds to 5/8. That's a lot.
Yes.
I'm not going to write it out because I wouldn't even know what to call it. That's a lot. There are an amazing number of seating arrangements that actually can happen in these 30 desks right here. Now, if you want to know for you 4 sitting here, since half our class is gone, take a permutation of 30, 4 at a time. What do you get there?
And that would include every single desk.
That includes every desk. So that means I can have it just like this, move Lily up 1, and that's a different seating arrangement.
There are 657,000.
657,000? There you go. So there are a lot of choices still. Right down here, looking at some notations, a permutation can be written this way. A permutation can be written this way. This is the one that we are going to use. A combination, this is the one we are going to use. It also can be written this way. And also this way. So we are going to see this one a little more often. We're going to see combinations written both ways. And sometimes we call it in choose R when we're talking about a combination. So you will hear that phrase, in choose R, it means it's a combination. So our in things chosen R at a time is the same thing as this. Just two notations, mean the same thing. Counting combinations. In the Miss America pageant, 51 contestants. Now wait a minute, I thought there were 50 states. Do you know why there are 51 contestants? Well, I'm not really sure, but I have a guess. Sometimes maybe Washington, D.C. is included. You do know that the capital is not part of any state. Or sometimes Puerto Rico is included, which is a U.S. territory, but not a state. I don't know what they're doing. 51 contestants are narrowed down to 10 finalists who will compete on a national television. And how many possible ways can the 10 finalists be selected? Now, this is first place, second place, third place, fourth place. This is simply, there are 10 from the 51. So I'll let you help me out with your calculators. You have a combination button, just like we have a permutation button.
1.27 times 10 to the 28. 1.28 times 10 to the 10.
Okay? There's a lot of different ways that can happen. Lottery numbers. The Georgia Lotto requires winners to pick six integers between 1 and 46. Now, when they said between, they actually meant including 1 and 46. The order in which you select them does not matter. Indeed, the lottery tickets are always printed with the numbers in ascending order, so smallest numbers on up. So they just want you to get the correct 6 numbers. How many different lottery tickets are possible? Well, we have 46 numbers. We are choosing 6 numbers. How many different lottery tickets are possible? 366,000. I'm the one writing it wrong. 366,000. 819?
Yes.
All right, well, let's beat the lottery system. Let's just buy one of every possible. You know, let's buy 9,366,819 lottery tickets, right?
Yeah.
Well, number one, you've had to purchase every one of those things if you are going to do every one of these combinations. And there's also another little challenge to it. How long does it take for you to purchase a ticket? I mean, even if you tell them, give me 10 of them, well, they've got to print out those 10 of them and then hand them to you. Let's say you can do it one every second. That's pretty fast. I doubt you can even do it one every second. I mean, you can't. But let's try this for just a moment and figure out how long a time period this is. Divide that by 60, because that would be how many minutes then. So if you take this number, if we said this is how many seconds, divide it by 60, that's how many minutes. Divide it by 60 again, we've gotten to hours. Divide it by 24, because, you know, all day, all night.
Oh, no.
How many days?
108 days.
That's 108 days straight, 24/7. I mean, that's not allowing you to sleep for 108. You're not going to be able to do this, even if you thought, I know how to beat it. Yeah, but no. Subsets of the M set. Let's try down here. Armando's Pizzeria offers patrons any combination of up to 10 different toppings. And they list all these things down there. How many different pizzas can be ordered, part A, if we choose any 3 toppings. So if we choose any 3 toppings, so on our pizza, does it matter the order that you put your toppings down on your pizza? No, not in this case. I mean, you may like the olives on top of the cheese than the cheese on top of the olives. I mean, but it's really the same thing that's going on. So we've got a combination of, from our 10, we're choosing 3. How many? 120? So you have 120 different pizzas you can make from simply 10 different options. So when you walk into the cafeteria and you say, there's no choices down here. Oh, yes, there are. That salad bar, I mean, there are thousands of choices that you can do in your salad in that salad bar right there. Different question. If we can choose any number of toppings, 0 through 10. Now, I'm going to explain it to you 2 ways. That means from your 10, you may decide to choose 0. That's one possibility. Or, and I would add, from the 10, you choose 1. Or, all the way down to, from the 10, you decide to choose all 10 of them. This is true, but there's a shorter way of getting the same answer out of this one. When you arrive at the bar, I don't know if you've eaten at Pieology in Siloam Springs, where, you start with the pizza and then you can choose whatever toppings. Well, when you see that first little bin, you have 2 choices. You're either going to take it or you're not going to take it. So when I walk up and they say, do you want pepperoni? I have 2 choices. I say, no, I don't want pepperoni. And then say, do you want mushrooms? No, I don't want the mushrooms. I have 2 choices, yes or no. Do I want the sausage? So far, my pizza's pretty plain. Do I want the onion? Ooh, I do want the onion. Now, how many times am I going to multiply this 2 together?
As many times as there are choices.
As many times as there are choices. 10 in this case. What is that answer? 2 to the 10th. So, and this is really what happens when you have your pizza. They say, what do you want to make your pizza? How many choices do you have? Well, I've got 10 of these options. You can choose them or not choose them. This one was, you are forced to choose 3 of them, and only 3 of them. You still have 120 options, but down here you have 1,024. So this is a technique that can be used if you have a certain set number of choices every time it's the same. Yes or no, yes or no, yes or no. So I have 2 choices, and I can make that choice 10 times, 1,024. So right down here, this is what they said. There are 2 to the n subsets of a set with n object, including the empty set, or if I can choose the entire set. So if it's yes or no, there are 2 to the however many yes or no's I can do. So down here, a national hamburger chain used to advertise that it fixed its hamburgers 256 ways. I think it was Burger King, but it's been a long time since I've heard that or seen that advertisement. Since patrons could order whatever toppings they wanted, how many toppings must have been available? Well, every topping I have 2 choices, yes or no. How many times am I going to make that choice? I don't know, but I do know that when I'm done making the choice, there are 256 options available. Do you remember what to do to solve for something like this? Yeah, I'm going to take log base 2 of that 256, and it will equal the number of times I can do it. Now, you might have to use a change of base formula. I'm going to use natural log of 256 and divide it by the natural log of 2, and what's your answer? Not very impressive, is it? All they really had was 8 choices to put on their hamburger. But they could advertise 256 different hamburgers you can make if you come visit us. It's true. It's true. But if you don't understand it, you think, wow, look at that spread when I walk into the store. And no, not wow at all. It's just in a little corner, 8 different options. There you go.